Everybody hear me? Okay. So as Andy said, I'm going to talk about moiré materials. And so please interrupt me at any stage. I'm actually producing notes, but they're not finished. And so I don't know exactly where I'm going. And maybe you'll influence that with some of your comments and questions. So this topic is an outgrowth of the of two-dimensional materials, started several decades ago now by 2 decades ago by Andrei Geim and Kostya Novoselov, who started to develop the techniques to take individual layers from bulk van der Waals crystals and measure their properties as two-dimensional crystals. And a natural outgrowth of that is to stack two-dimensional materials on top of each other. And there are many interesting things you can do in that way. And I'm going to be talking just about one of them. And that is what happens when you have a moiré pattern. So I'm going to come back. Whoops, that's me. I should turn the internet off, maybe. Okay, let's hope that doesn't happen every 30 seconds. The first two material is graphene, a single layer of a graphite crystal, which forms a honeycomb lattice. I'm going to come back and remind you in just a moment about some basic properties of honeycomb lattices. If you take two graphene layers and lay them on top of each other and make these two-dimensional crystals very similar but slightly different from each other by twisting, then you can see that you get a moiré pattern. You get a periodic pattern. Basically, the stacking between the two layers varies periodically. The length scale of this stacking periodicity is, in this case, inversely related to the twist angle, and therefore it's controllable. So what we'll be talking about is the fact that these moiré patterns populated by carriers in this semi-metal act like two-dimensional crystals. They're at, what's special about them is that at the present moment in time, as you heard in the last talk about making nanostructures, this is the best way to make artificial periodicity on the 10 nanometer scale. Okay, so maybe you can do it lithographically, but when you do, your feature shapes will not be identical or very identical, sufficiently identical from feature to feature. So, yeah. So these are artificial two-dimensional crystals, and 10 nanometers is important because that's just the right length scale. It's sort of the it's the shortest length scale at which it's still possible with electrical gates to change the number of electrons per period of this pattern, per unit cell of this pattern, by numbers that are bigger than 1. So as we'll say, we can make certain specific and, turns out, interesting types of artificial two-dimensional crystals, and we can change the number of electrons per atom in these crystals just with electrical gates without introducing disorder. And what we have learned about these materials is that their electronic properties are extremely rich. I have this sort of prejudice that the electronic properties of real crystals are probably mostly just as rich, except that the behavior at fractional numbers of electrons per unit cell is always obscured to some extent by disorder, okay? Okay, so I'm going to talk about, I'm not going to survey this whole subject. I'm going to talk only about twisted bilayer graphene and twisted transition metal dichalcogenide homo bilayers. They have been very interesting examples, so they're good ones to talk about. And I'm not going to review all of the very large literature on these two different topics. Instead, what you will get are my prejudiced opinions. And you are very welcome to chip in with your opinions as I go along. Okay. So let's start at the beginning then. I want to make one property, one observation about the properties of an isolated graphene system as a two-dimensional crystal, because it informs one of the prejudices I have about the properties of twisted bilayer graphene. Okay. So let me write down here on the blackboard. It's okay. There's the crystal structure of graphene. These are all carbon atoms. I painted green ones, which I called A carbon atoms, and orange ones B carbon atoms. The green ones and the orange ones separately form two-dimensional triangular lattices. So each green atom has 6 green near neighbors, and I've reminded you here about the primitive lattice vectors of the triangular lattice, and reciprocal lattice vectors defined so that G1.A1 is 2 pi, and G2.A2 is 2 pi, and G1.A2 is equal to 0, etc. Oops, where did my pointer go there? By the way, I have an ankle injury. A week ago, I couldn't walk. So I'm doing very well here, but I might have to ask one of you to bring up a chair at some point. Let's see how I get along. Okay, so here's the lattice structure of graphene. And this is the electronic structure of a graphene sheet, actually understood since the 1940s, when people started to think about graphite as a moderator material for nuclear reactions. And you can see that energy versus momentum in the microscopic Brouin zone of the material. And there are red bands that are further away from the Fermi level. These are actually the sp2 bonding and anti-bonding orbitals that give a graphene sheet its exceptional stiffness and strong bonding. And still moderately wide are these blue so-called pi bands. So these are formed from the p orbitals that are pz in the plane of the graphene, that are oriented perpendicular to the graphene plane. And there's one, of course, one of these orbitals per each carbon atom. So we have, this is a honeycomb lattice. It's not a triangular lattice. There are red or green sites and orange sites, A sites and B sites in each unit cell. And each A site has 3 B near neighbors and vice versa. And the 3 vectors that connect a lattice vector to its near neighbors, the vertical ones, tau1 I called here, tau2, tau3. And so those are the near neighbor distances. These 3 vectors all have the same magnitude if you check, and they have a relative orientation of 120 degrees in the honeycomb lattice structure. And so I'm only interested in the blue electrons. I can make some sort of LCO or binding model with just pi orbitals. Let me write down the Hamiltonian and tell me if this writing is big enough. The block Hamiltonian Uh, and so here's a tight binding model with just nearest neighbor hopping. You'll notice that the near neighbors of the A sublattice, so this is a 2 by 2 matrix, an A sublattice part, a B sublattice part. All the near neighbors of the A's are on the B sublattice and vice versa. So this explains the magnitude of this off-diagonal term gives the k-dependent splitting between the two pi bands. And since there are, there's one pi electron on each carbon atom, so we have enough electrons in a neutral graphene sheet to fill up, 2 pi electrons per unit cell. So one of these two bands is filled and one is empty, okay, if they don't overlap. And so the splitting between the bands is k-dependent. And this quantity, you can easily check, vanishes at the corners of the Brouin zone. So these are the 2 points I've labeled over here, K and minus K. If I construct a Brouin zone the way I've done it here, K and this point in momentum space and this point in momentum space, those are actually separated by reciprocal lattice vectors of this structure. One of the reciprocal lattice vectors is in the y direction, as I wrote on the blackboard. So K is split in this Brouin zone between these 3 points. But there's another inequivalent Brouin zone corner wave vector at minus K, and it's split between these other 3 endpoints, right? So we're going to be interested in electronic properties at low energies, let's say within an EV of the Fermi level, and it will be very important for everything we discuss that all of the states we're interested in, all these low energy states, are formed from wave vectors that are close to the Brouin zone boundaries, okay? So for low energy states in neutral graphene, we can expand this. It turns out that this hybridization between the A and B sublattice pi electrons vanishes right at the Brouin zone corners. If you expand this around the Brouin zone corner, the expansion is linear. And so this becomes it turns out the expansion goes like kx minus iky. This t here is a near neighbor hopping parameter. Over here, I've expanded the expansion around the Brouin zone corner as a velocity because this linear expansion coefficient, if I stick in an h bar, has units of velocity. And this parameter is actually the slope of the energy versus momentum lines near the Brouin zone corner. And for what will, whenever you see a 2 by 2 matrix, it's a pseudospin. And so it's natural to think about this as sublattice pseudospins in a graphene sheet. And if I do that, if I write the Pauli matrices, usual Pauli matrices in this 2 by 2 sublattice space, then you can see that this Hamiltonian is proportional to sigma dot k, okay? So the block eigenstates are spin a half spin coherent states. There are states where the sublattice pseudospin is either directed parallel to the momentum or opposite to the momentum. Yep.
T times A.
With some coefficients like a root threes and so on. Yeah. Yeah. Yes, exactly. And V, it turns out, is around 10 to the 5th meters per second, okay? Which is kind of a metal velocity. That's typical velocity of an electron. Ooh, I said that wrong, 10 to the 6 meters per second. That's the typical velocity of an electron in a metal. And 300 times slower than the speed of light. So unlike, so these are, it's a gapless semiconductor, if you like. And because gapless, you don't have parabolic dispersion at the band extrema. You don't have small velocities near the band extrema. And so this velocity is set by the entire biband width, which is actually sizable. So you get high velocities. Okay. So, in the literature on graphene and for thinking about the properties of the graphene, we mostly think about this pi band tight binding Hamiltonian in terms of its small wave vector expansion. And maybe I won't belabor this point. But these, expansions of Hamiltonians around band extrema are often very useful in talking about semi-metals or semiconductors. And you can think about this as a K dot P Hamiltonian, where if K just becomes minus I grad, as in usual quantum mechanics, then what you get by solving this then continuum Schrodinger equation is actually the envelope functions of the pi orbitals on the carbon atoms, which are, since we're interested in distances that are much longer than an atom, it's really these envelope functions, which are kind of a coarse-grained description of the wave function, which are the efficient way to think about properties. Okay? So the eigenstates then are spinors. They're momentum eigenstates, and they have two components, a component which is the projection of the envelope function on the A sublattice and a projection on the B sublattice. And I'll stop saying envelope function and forget about the fact that there are actually atomic scale orbitals underneath, okay? Okay. So graphene, in 2000s, as people gradually learned, people like Philip Kim, who's here and will lecture again this afternoon, and also Geim and Novoselov and their collaborators and others got better and better at making more and more perfectly isolated graphene sheets with weaker and weaker disorder. And graphene became like a new version of the two-dimensional electron gases. And when I say electron gas, I mean that the non-interacting eigenstates are momentum eigenstates, free, like free particle wave functions. So it became, a new version of gallium arsenide, which people had studied, for decades and discovered lots of physics motivated by the discovery in the 80s of the quantum Hall effect and the fractional quantum Hall effect and many other things that arose in semiconductor quantum wells as the years went by. But So graphene was different. It turns out that typical semiconductor quantum well is about 20 nanometers thick, and that thickness reduces the scale of the Coulomb repulsion between electrons. So one of the things that's different about this new two-dimensional electron gas is that the interactions are stronger. But the single particle energy scale controlled by this large velocity is also stronger. So it turns out that if you put carriers, if you go away from neutrality in a graphene sheet, you get a two-dimensional Fermi liquid, just like you get in a semiconductor quantum well. For the most part, the strong correlation physics occurs in a magnetic field in graphene sheet. So new version of the quantum Hall effect, new version of the fractional quantum Hall effect. Very importantly, in terms of recent research, graphene two-dimensional electron gases, or bilayer two-dimensional electron gases, at least, are seemingly the most attractive place to make non-abelian fractional quantum anomalous Hall states. So graphene is different from semiconductor quantum wells in a number of interesting ways, but for the most part, it's kind of qualitatively similar. Okay, and the Moire materials we're going to be talking about are not similar at all. They have extremely complicated and rich and interesting phase diagrams that are mostly not understood, and that means that they're open for you to understand. Okay, so but I wanted to start by mentioning one thing that's different graphene compared two-dimensional gas and semiconductors. It's to the fact that you may be familiar with the property that the spin magnetic susceptibility is enhanced by electron-electron interactions. And if it's sufficiently enhanced, it can produce ferromagnetism in metals. It turns out that in graphene, the spin susceptibility is suppressed by electron-electron interactions. And so I want to explain why, because it turns out that that's going to be related to, perhaps related, or I will suggest that it might be related to some of the features of the twisted bilayer graphene, the Moire material phase diagram. Leo?
I was wondering, at a non-intellectual level, are there any consequences of once you find it doping? Is there any consequence of the Dirac point?
Yeah. So yeah. So there are some consequences of detail revealed mainly when you apply a magnetic field. For example, one of the Landau levels gets stuck right at the Dirac point. Also, both of these systems become interesting or become complicated when the Fermi surfaces become very small. And for a semiconductor quantum well, it's expected that the electrons will form a Wigner crystal state, right? The Fermi surface will disappear, you'll break translational symmetry. Graphene, when its Fermi surface gets small, becomes complicated in a different way because even down to low temperatures, the scattering of electrons in the band you're studying and the other band, which is not separated by gap. Let's say if you put carriers up here and make the Fermi surface smaller and smaller, the fact that these electrons are here matters. And
I guess also if you have a quadratic spectrum, conventional semiconductors, the Coulomb energy
will become dominant.
Yeah. They scale the same way. They scale
the same way, that's right. And it seems, and they scale the same way as the density gets low. And roughly speaking, if you ignore the presence of the other band, the fact that this velocity is so big means that it dominates and interactions can be treated perturbatively. Okay, so that's the so-called fine structure constant of graphene, which is E squared over, h bar, this velocity v Dirac, which turns out to be of order 1, but of order 1 is still just a little bit below maybe where things get interesting. So it's a fairly strongly interacting system, but not apparently, we know from experiment, not strong enough to make anything interesting happen on its own. Okay.
Dielectric constant we don't find there.
Yeah, and so that depends on the what the surrounding material is, what the dielectric environment is. Nowadays, typically HBN, which has a dielectric constant around low. You can also suspend a graphene sheet so that there's very little dielectric screening, and that makes the interactions even stronger. But I think experiment says, that in single layer graphene, the most obvious thing to happen is you get some broken symmetry that opens this gap, right? And that seems not to happen. Just as, okay. Okay. So let me do a calculation. I'm going to calculate the self-energy of electrons in the conduction band due to just due to exchange. Okay, and so this is in terms of Feynman diagrams, it's this self-energy, and let's say, for example, let me assume to start this that I want to calculate the exchange self-energy of a conduction band electron when the valence band is filled. And so this this self-energy is familiar, and we know it's there's a contribution from all of these occupied states, and let me keep the momenta of those occupied states discrete for a moment. So if I wanted to calculate the self-energy, I'm going to sum over all k's in the valence band, and then I'll get an exchange matrix, a two-particle matrix element. Where and one of the two particle states exchange the two particles. And so that's just, complete expression for self-energy in some system, but something interesting happens because of the sublattice spinners that are the eigenstates of this 2x2 equation, right? There's the wave functions have spinor components. So please stop me if many of you here, I know, hi Aiden. Aiden, we have to finish that paper. Let's talk about it. So some of you are very familiar with this, but don't hesitate to stop me if you're not. To a good approximation, so this is the Coulomb interaction. It acts on the orbital degrees of freedom. Each of these states is a two-component spinor. it's, let's say K. So this is a coordinate sublattice. Let's say the conduction band orbital. Has a plane wave part because this is an electron gas, but it also has a sublattice part. Okay. Oh, yeah.
In the large country.
So I'm neglecting the Hartree contribution. When I'm doing that, I'm assuming that this is a uniform density state. That's all. So there's the usual trick as, you can say that, that's the usual thing. Turns out that in all of these, they're all dual gated, as I'll talk more about later. And so the neutralizing charge is actually on the gate. So
Shifts the chemical potential or shifts the.
in this case, it will just shift the chemical potential, if you like. Yeah.
For the Green's functions, this would be, that diagram, if you write it, it'd be convolution between V and the Green's function.
Yeah.
Integrate over omega and get to this expression.
Yeah. So when for this simple diagram, if I put in the bare frequency independent interaction, then the frequency sum gives you a Fermi factor. And I'm summing over here over all the states K prime in the valence band, right? Because I'm just assuming for the moment that the valence band is completely filled and the conduction band is completely empty, like in this picture. Yep. Square one.
Thing in the sum.
So so this is a two-particle matrix element, which comes, one in this two-particle matrix element is, let's say, at this vertex, particle two vertex. Is that what you're thinking about, the two vertices?
Hamiltonian, the interaction. Part of the Hamiltonian. This is like first order.
This is the first order in perturbation theory, yeah. Okay, yeah. If this was electron phonon scattering, this would be a phonon propagator, and you'd have some electron phonon matrix element, and that would be squared. But something will get squared in a second. Okay, so this Coulomb interaction, because we're assuming all the length scales are large, doesn't care what sublattice the electrons are on. It's just a 1 over r minus r prime interaction. So it does not act on the sublattice degree of freedom of these spinners, okay? And so what you get for the exchange interaction is from the orbital part, you get, because these are plane wave eigenstates, you get the Fourier transform of the 2D 1 over r interaction at the difference between these wave vectors. And from the orbital part, so this is these spinners I was talking about before. They're K-dependent. And, at vertex 1, you get the spinner with the conduction on the left the way I've written it. And at vertex 2, you get the complex conjugate of the same thing. Okay, so it's this spinner character that is different from an ordinary electron gas. And as I mentioned, these spinners are spin coherent states. Those are the, for spin a half states, the states whose pseudospin is in direction k, and this This index should be K prime, right? So this is the inner product squared between a state aligned along the direction K and a state aligned along the direction K prime. And you can easily check, that, for example, if these were, this state is along the direction K prime, but the conduction and valence band states are point in opposite direction. So this is actually along the direction minus K prime because it's valence band. Okay, so this you can easily do a little calculation and show that this inner product square just depends on the angle between K and K prime. If K and K prime are the same, then these spinners are spinners for states at the same K, but they're valence band and conduction band, so they're orthogonal, okay? So this matrix element will go to 0 for K equal K prime. Yep.
Say more detail, so he inserts or we insert an identity in terms of these R alpha states. That's what the matrix element of B is in central sandwich between two different alpha crossing levels, is that right? And then would the result be 1 over R minus R prime dependent of alpha and beta, or would there be like a delta alpha beta?
Yeah, I think I understand your question. Okay. So let me do something slightly simpler. Let's say I wanted to calculate a matrix element of some sublattice independent operator, that single particle operator, which was a potential operator, okay? Potential operator. This is sort of 1/2 of this calculation, okay? So one way to think about this is, here's this written in the convenient eigenstate representation of these plane wave states. But let me write it in a coordinate representation because the interaction is simple in a coordinate representation. So I can say this is integral dr, K conduction R, putting in a complete set of states twice. Okay. And this is R prime, and I have to integrate over prime.
Is there an alpha?
I can put those in if I, yeah. Thank you. Okay, that's sort of what you had in mind, right? So this, should be a product here, because all of these quantities are, states in this product of orbital space and sublattice space, right? This potential operator is sublattice independent. And, coordinate representation is convenient for interactions because interactions are local in a coordinate representation.
So there's no delta alpha.
There's a delta alpha beta right here.
Is there?
Yes, yeah, because this operator doesn't act on sublattice. It's sublattice independent.
Okay, but I'm just having trouble visualizing that because like, if I have, over here, but on the A sublattice, I have electron, and then over here I have another one, but it's on the B sublattice or something like that.
Yeah.
There's still gonna be a Coulomb attraction.
Yeah, there's a Coulomb interaction between them. It doesn't care what sublattice state they're in, right? So here I put a complete set of sublattice states on this side, complete set of sublattice states on this side. This operator doesn't act on sublattice. So this inner product gives you a delta alpha beta. That makes sense. Let me go to the end, okay? And so this this is then sum over alpha. I put in the normalization factors for these plane waves. Now I have only one position to integrate over. This is the complex conjugate of the wave function. And I have chi alpha k star. Over here I have, because of the delta alpha beta, I have chi alpha k. And V of r, whatever it is, and e to the chi k prime. Does that make sense? Okay. And so we're just doing that at each vertex of this, if you like.
It's not an that matrix it's not representing interaction between particle at position R.
Yeah.
And particle at position R prime.
Yeah.
And sublattice alpha and beta. It's really single particle energy.
So this example is the single particle example, but it's the same thing except doing it at both vertices R and R prime, which I was, being.
I got it.
Okay, so now I'm going to erase this. Okay. 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 So the thing that comes from the sublattice structure is this 1 minus cos theta. Okay. Yeah. And so let me calculate this self energy at k equals 0, okay? Actually, there is degeneracy between the conduction band I'm calling this positive energy band, and valence band negative energy using semiconductor physics jargon. There's actually a degeneracy, k equals 0, but it's not going to matter. Let me not belabor this. You can see that if I do k equals 0, then well, let's say k is infinitesimal and in the x direction, okay? Then when I sum over k prime, I'm going to get something that diverges, right? If I just set k equals 0 here, I have 1 over k prime, 2D integral of 1 over k prime. So that diverges very strongly, linearly with the momentum cutoff. But, that's what we should expect because, we're using a model. We're only interested in the states up here, but really there's there are exchange contributions due to all of these electrons down here, and indeed all of the red electrons too. And so the k equals 0 term is just some constant, right? They're in fact, which is like a chemical potential shift. It doesn't matter. Okay, so let me look at sigma of finite k, and I'm going to take k to be in the x direction, minus sigma of k almost equals 0. We're only interested in the k dependent. It's going to take it to be in the x direction. And I'm interested in how this self-energy depends on the state. And so I want to do an expansion at small k, okay? And so it's 1 over a, almost everywhere in the integral. And let me, write this integral, this k now as an integral. And I have this factor that comes from the spinors. Okay. And then I have 1 over k minus k prime. And almost everywhere in the integral, k is small compared to k prime. So I can write this as 2D Fourier transform, 2D Coulomb interaction in momentum space, Fourier transformed at wave vector k. And the correction to the denominator here due to Coulomb interactions, I'll expand to first order in k, and it becomes 1 plus k over k prime cos theta k prime. And theta is in the x direction, so that's just theta k prime. So I've expanded, the absolute value of 1 minus vector k over k prime to first order in k. And did I forget a factor of 2? So when I do this integral, there's the k equals 0 terms, which we've already agreed to throw away. So I'm not going to include that term. I have the linear in k term here. And signs are coming out wrong. Is it? Okay, thank you. But I think there's a sign wrong. Yeah. Okay, so I'll proceed in a while. Let's see if I. So this integral, when I integrate over the angle of k prime, a factor of cos theta here, it's cos squared theta, and so the integral over angles of cos squared theta, because of this fact, is not 0, it's pi. So I have integral dk prime k prime from 2-dimensional momentum space 2 pi e squared over k prime, k over k prime, and n pi. Okay. Yeah.
First line.
Yes, correct, correct. Well, minus cos theta. So I haven't, yeah. Yeah, this is also K prime. Okay. So, yeah, so this gives, so what you get for the self energy is E squared. Typically there is some dielectric screening, as already been mentioned, which I can restore in the background. It's linear in K, and it's integral dk prime. I've gathered together powers of K prime, 1 over K prime. So I have a logarithmically divergent integral. And let me shift this up a bit. And, I can cut this off wherever I like, somewhere deep in the Brouillard zone, okay? Let's say I cut that off at 1 over lattice constant. And let's say, let's say I'm trying to evaluate this not at K equals 0, but at some finite K in the conduction band. Then it turns out that some of the approximations I made broke down. And this, I no longer have an integrand that's diverging like 1 over K. So the end result of this calculation is that there's a positive contribution to the velocity which grows as K goes to 0. And so if I plot with this correction, with this exchange correction, what E of K looks like, the non-interacting result is the one I derived on the blackboard there. E of K is H bar VK. Deep in the valence band, all of these energies are reduced by an exchange interaction. These are valence band electrons, and I have exchange interaction with occupied valence band states. And what this calculation is, let me just, if I go high up in the conduction band, and if I look at some K, then with a 2D Coulomb interaction, the states that contribute to the self energy are dominantly those that are states in the valence band that have nearly the same wave vector. And those states are nearly orthogonal, okay? And so that means the self energy, exchange self energy goes to 0 up here, and its slope, what this perturbation calculation says is the slope of E of K diverges logarithmically, right? Close to K equals 0. So this effect is the effect of interaction in graphene. It's very obvious experimentally, and it's actually something we'll come back to maybe later, is that, people say the velocity Dirac, according to ancient fitting going back to the 1950s, like typical, try to use a larger value, 3 value, I quoted there, about 20% increase, and that is simply mainly just this contribution at some typical wave vector level, and people are looking at some 12 per square centimeter. Yeah, go ahead. So this is E, including the interaction, and this is K, and this is 0, right? So this is the Dirac point. So this would be the Fermi energy of a neutral system.
Well, much larger.
Yeah. So the velocity is enhanced, even at typical density, the velocity in graphene. Well, yeah, this is first order perturbation theory. People have tried to look at, what happens if I sum up all the divergences to all order, and then you can, the conclusion that has least been reached is that the energy goes, this interaction, self-energy correction goes like a power of K that's smaller than 1. So the logs add up to a change in the power law. But that can't be seen experimentally. Go ahead. Let's say I do this for example, for a valence band that's not completely filled. So I'm only summing over occupied states. That can give me a cutoff. Or yeah.
Well, because it's also when he integrated over K prime, he ignored the K, the denominator of, he expanded, you ignore the K inside the denominator.
Yeah.
But if you didn't, then it would function of the cutoff.
So it is the same K.
It's that K.
Okay, so but what this says, I can do a similar calculation and move the Fermi energy around and calculate the self energy at the Fermi wave vector. It has a similar looking curve, okay? And so the Fermi velocity is, the chemical potential is in the energy, including a self-energy correction at the Fermi energy. And that chemical potential is increasing very rapidly with density near neutrality. And what that means is the system almost has an energy gap. If I had a real energy gap, the chemical potential would jump. And when you have an energy gap, I think if you can make an energy gap, it lowers the energies of the occupied states, like we see here, and that makes the system stable. Okay, and so the system likes to sit at half filling, and the fact that these if I look in 2D momentum space now and look near a Dirac point, the sublattice pseudospinner which has an A and B component, changes with the orientation of K. That means it changes very rapidly with K around circles in K that have small magnitude. And that's bad for exchange interactions. So from interaction point of view, a system doesn't like to have, sublattice spinners in this specific context that change very rapidly with momentum. So we're going to be talking about in this more off topological bands. Wave functions are changing rapidly, changing with momentum, and interactions just generally don't like that. They don't like topological. But okay, so I'll come back to this point later. Okay, go ahead.
Electron count of the exchange. You also find a logarithmic divergence at the Fermi wave vector with the
Yeah.
interaction.
Yeah.
So what's different here? Like, how come that calculation actually like
It's not logarithmic, it's not logarithmically, this is first of all not cured by screening. And secondly, it's logarithmically divergent, not at the Fermi energy, but at the Dirac point.
okay, independent of as you dope the system?
If you dope it enough logarithmically. Yeah, go ahead. Yeah, so exchange energy is negative. Yeah, because it represents a correction because the many electron wave function is antisymmetric. So that antisymmetry always reduces the repulsive Coulomb energy. That's why it's negative. Yeah, so this correction at finite K, this is the self energy minus the self energy at K equals 0. And that's positive. And yeah, so changes. I won't go into this, but this actually means that interactions suppress the spin susceptibility rather than enhancing it. And I'll come back to something about this when I talk about twisted bilayer graphene soon. Go ahead.
When you say that this is not cured by screening, what do you mean? Because, if I had an interaction that didn't diverge like 1 over K prime, then the integral wouldn't be log divergent.
Yeah, and but there's no screening at the Dirac point.
Okay, the density of states is good.
Yeah. Screening, the polarization function is actually vanished linearly with K. Okay, so I took predictably much longer than I planned, and but I will come back to that point, and let me turn to something different. And I might not finish, but maybe I'll try. So now we're back to single particle physics, and we want to take account of how do these two layers influence each other when they have a finite twist angle, and so let me try to calculate the matrix element between a state K, and so imagine I'm using a pi orbital type binding model with with 2 sublattices. So there are 2 orbitals I'm interested in. So I can make basis states in that pi orbital type binding model, which have a definite block wave vector, and alpha here is standing for a sublattice index. Okay. And imagine that I have, if I have these 2 layers close together, then I can tunnel between the layers, and I'm using label P for a state in the for a state in, let's say this is a state sublattice alpha in the top layer, and so this is top layer for top, and this is B bottom layer state, right? So in this continuum K dot P model, I have spinor wave functions. So arbitrary wave functions, I'm using a momentum representation. Or right here, I'm still with the tight binding model. Okay. So, so let's say, this is some tight binding model wave function. And let me write it as, let me expand it in terms of localized pi orbitals on each site, okay? So here I have a sum over the lattice vectors, and I have normalization factors. So this is a sum over the lattice vectors of the A sublattice, or of the top layer. And so when I make a block state, I put in this factor e to the I k'd up the position of the orbital, choosing, that's a gauge I can choose. And for the tight binding model state in the other layer, which is rotated and therefore it has a different crystal, I have to sum over the lattice vectors R prime of that crystal. And when I expand it, I have these, block phase factors, and then I have some matrix element. Let's call this tunneling. Okay, is that clear for everybody, what I'm doing? So you can think of it as a tight binding model. You can think of these as Wannier functions, if you like. And so this is a pseudo block wave function in the top layer on sublattice alpha, bottom layer sublattice beta. To write down these wave functions, I have to recognize that I've rotated the lattices. So this, the lattice vectors R prime are slightly different from the lattice vectors R due to the rotation. And this is some hopping between pi orbitals in different layers on different sublattices and in different sites. And for this, I'm for the moment, I'm going to make a two-center approximation, and basically assume that I have these two pi orbitals centered on different sites, and they're on different layers, so there's a separation between them vertically. But the hopping between them, doesn't know about any other atoms. It can only depend on how far apart these two pi orbitals are. So this function here is a function of the projection of the difference between the two positions projected to the same onto two dimensions. Okay. So a little bit later, it's not going to be today. It's clear to me that this approximation here is not essential at all. But this is actually the first way we did the calculations that give you a convenient continuum model for the twisted system. Okay. Yeah. So basically that's what these are. So you can think of this in a K dot P way. and it doesn't really matter. In which case, this is a wave function labeled by a site R, and it can be the periodic wave function at in the cell that's labeled by this lattice vector.
That's a periodic, that R is a periodically extended, or is it a 1 year function?
You can think of it either way. Okay, it's not going to matter. So I was describing it as a, basically LCAO language, or more modern version of that would be Wannier function language.
Sorry, I'm a bit confused about what the taus are. Those
Yeah,
taus are
so
not-
I should have said, so this is referring back to the beginning. So let's say I have the A sublattice and I have a triangular lattice vector. That's what the vectors are lattice vectors that connect the green points. The taus are, I can choose one of these B lattice points to be like this one, for example, that's separated in the Y direction. And when I translate that also by all triangular lattice vectors, I get all the sites. So tau is a 2D vector, which is either 0, or it's the vector that connects position B to position A. Okay. Yeah, thank you. I should have said that. Okay. Yeah. Yeah. So this is so now I'm talking about basis functions that are on a particular sublattice. Okay. So this is the hopping operator in the sublattice representation, if you like. That makes sense? Anything else? Any other questions that can make it clearer? Okay. So let's say I have this function. It's a function of a 2D coordinate. Let me just say it has a Fourier expansion. So this is 1 over n, and I'm going to Fourier expand it. And so I have sum over r prime, and q, and the Fourier coefficient of the expansion of this unknown function, I'm going to call it little t, t for tunneling, and I'm going to label it by q. And then let me bring all of the phase factors together. I have this phase factor, e to the minus ik dot r plus tau alpha. K is a wave vector, of the state in the top layer, e to the ip dot r prime plus tau beta. And I put a prime on this tau because I'm imagining that the bottom layer has been rotated. And then I have, from this Fourier expansion, e to the iq dot r plus tau alpha minus tau beta. And so now I can sum over lattice vectors R. Okay, so our lattice vector R appears here, here it's multiplied by minus K, here it's multiplied by plus Q. And remember, the basic thing you'll learn about Bragg scattering and reciprocal lattice vectors and so on is that sum over all lattice vectors of phase factors, e to the I k dot lattice vector, is n, the number of lattice sites if the wave vector is a reciprocal lattice vector, and it's 0 otherwise, okay? So that tells me then, by summing over R, K is equal to Q to within a reciprocal lattice vector. A reciprocal lattice vector of the top layer. Summing over R prime, P is equal to Q to within a reciprocal lattice vector of the bottom layer. And so this is equal to actually I get 1 over A naught. I have 1 over n times A, and I have two factors, n, the number of lattice sites, and n divided by the entire area is 1 over the unit cell area. And I can write everything as, sum over G, G, G prime, and Q, TQ, and then I have delta Q is equal to G, a reciprocal lattice vector of the top layer, and delta Q, and Q is also equal to G prime. Sorry, this should have been delta Q K plus G, delta Q P is a wave vector in the other layer, plus G prime. And then I have the factors, tau alpha, and Q minus K is G, so it turns out you get e to the I G dot tau alpha minus G prime dot tau beta. Okay, so tau is 0 for one of the two atoms in the unit cell, and is equal to that vector connecting nearest neighbors in the vertical direction for the when the label is the other atom in the unit cell. So one sublattice has points on the lattice, triangular lattice sites, and the other sublattice is separated by tau. Okay. Yep. Tau prime. So it's slightly rotated, right? Yeah. Go ahead.
Sum you used in the second line of Q is just an integral over all Q.
Yeah, yeah. Sum over all Q, and the Q are unrestricted because it's a Fourier transform of this arbitrary function. Yeah. So, what this says is that, Q here is, the change of kind of change of the momentum K. So there are two sets of reciprocal lattice vectors, G and G prime. They're slightly different from each other. And so the set of matrix elements that are, this is a one body operator. The set of matrix elements that are different from 0, if is not that of a crystal, if I include all of the terms in this sum. It's that of a quasi-crystal because I have two reciprocal lattice vectors, G and G prime. So these Moire systems are generically quasi-crystals. But there's a set of terms that are dominant that are like those of a crystal. So we're interested in the tunneling matrix elements between low energy states. That means K has to be near one of these Dirac points, near one of these band crossing points, near one of the reciprocal lattice vector corners. P does too, right? So K and P need to be nearly the same. And so the only way for K and P to be, nearly the same is if the reciprocal lattice vectors G and G prime are the same up to a rotation for this twisted case. And so if I pick a reciprocal lattice vector G, then G prime has to be the rotated version of the same reciprocal lattice vector. And
It seems like G prime is rotated, but it has to differ from G by reciprocal lattice.
okay, let's see, where's my, time to change slides. Woke it up. Okay. So these are the two reciprocal spaces. They're slightly rotated relative to each other. And if, for example, I write this, if I choose the term in this sum where G and G prime are both 0, and let's say K and P are both near this Dirac point, and G and G prime are 0. It's one of the terms in the sum, okay? And so that would mean that P has to equal K. And the Q that's here is the Q of that K. So what this says, is that it makes sense that this tunneling, the way I've written it down in this model, depends only on the difference for these positions. So it must conserve momentum, right? But the two layers are rotated relative to each other. The Q that is here is close to the Dirac point, okay? And so if I go over here, here are the two Brouin zones, and the twist is exaggerated here. This is the K in one layer, K in the other layer that's rotated. And you can see that if I tunnel anywhere in this region, I have momentum with the G prime equals 0 term. And the coefficient of that process is the Fourier transform of this function at the Dirac point, okay? So all of this, I can take, if we're only interested in points near the reciprocal lattice vector, then for G equal G prime equals 0, I can take that outside and replace it by the value of this function at the Brouin zone corner. The tunneling from layer to layer is on atomic scale non-local. And basically, the wave functions do this Fourier transform of the tunneling function. Okay? Okay. So I'll try to reach an endpoint in 5 minutes. I will take no questions. Yeah. So this function T of Q the G equal G prime equals 0 term in this sum is it's at some wave vector, which is the Brouin zone corner wave vector. And this function, if you Fourier transform it, the layers are far apart. The lattice constant within a layer is short, and this function will go down very rapidly. So we're only going to keep this smallest value of Q, smallest value of K and P, if you like. Now, this process has, a given K in one layer hops to the same K in the other layer for G equal G prime equals 0. But if I choose, and this is normally the gauge we choose, to measure momentum from the Brouin zone corner in each layer, then this process actually has a momentum transfer, and the momentum transfer is just the difference between the two Brouin zone corner momentum that that is present because of the iteration. And that momentum transfer, let me just write it here. The momentum, the momentum change due to rotation of a state at the corner of the Brouin zone is the magnitude of that vector for small rotation angles times the rotation angle. And if I choose K to be in the X direction, then this Q is in the Y direction, okay? So that's K is at the Brouin zone corner. The G equal G time prime terms gives, Q equal basically Dirac momentum. But if I start from the Dirac momentum, there are two other G's, which give you a Q of the same magnitude. If I go back up here, is it still there? Yeah, so if I go from this red A point and translate by a reciprocal lattice vector over here, the magnitude of this K point and this K point are the same, and the same in the other layer. So it turns out those other two regions of momentum space have the same Q, and therefore they have the same coefficient, which I can take outside the integral, except that the Q's are rotated by 120 plus or minus 120 degrees. Okay, so there are two final points I want to make. I might say 1 minute over. Basically, for every G, if the only other G prime I keep is the one that's just the rotated version, slightly rotated version of the same wave vector, then all the momentum boosts will end up being small. And that gives you the restriction to G prime has to be the partner of G, gives you a periodic model, okay? And if I specifically, take advantage of the fact that this hopping function is liable to be smooth on a Moire scale, then I can pick out the three dominant processes, which in this gauge are three momentum boosts, which I've called for hopping from one layer to another, which are three equal magnitude wave vectors, small wave vector boosts, proportional to twist angle that describe the pattern of tunneling from one layer to another. Okay, let me stop there, and anybody who's interested can ask me questions for as long as they like. So thanks. We'll continue. Why does it decrease rapidly? So this function, I can say, if I imagined I use some, Slater-Koster two-setter approximation where you have hopping integrals that depend on dimension and on direction of hopping. right? And but here I've so this really, the magnitude of the distance between two layers is the 2D distance plus the distance between layers, okay? And so the layers are much further apart than the lattice constant within a layer. Typically, graphene, I think it's 3 times further apart. And so when, this function as a function of this variable, this plus d squared, if you like, rounds out anything that's sharp. So it's a smooth function. So its Fourier transform goes down rapidly. Somebody over here asked that question. Did that answer make sense? Yeah, there you are. That made sense. Yeah. So in fact, you can take some, generic model or, just a guess at what this function looks like, and you find that it goes down very rapidly. So that the next value of Q that's relevant, if I keep all of the G terms, but still insist that G prime be a partner of G, then the value, turns out the value of this term is around 100 MeV. That's the basic energy scale. And the biggest ones are about 1 MeV. Yeah, it turns out the gaps of the lowest order commensurate angles between the layers. Yep.
You have to do up points and they're shifted. So then if you conserve momentum as you tunnel, you're now resonance, like you start out.
Yeah.
You no longer have a state there because you.
Exactly.
So where's that contained?
That's in these momentum boosts, right? So this is, so if you describe it that way, then if I sit at the of the blue lattice, blue layer, end up at this point, at this same point. If I start in the red layer and I tunnel to the other layer, in one gauge choice, I'll end up at the same momentum. And you can see I'm basically far, and this far is the vector Q. This far in momentum away from the Dirac point of the other layer. But I'm always
See, in
yeah.
this gauge, if I now evaluate the diagonal contributions, I guess, the contributions of the energy for each layer, not the tunneling pieces, but just the kinetic energy. If I look at the kinetic energy
difference,
then there'll be kinetic energy difference.
Yeah. So that's of course that statement you just made is gauge independent, and that energy, is h bar v q.
Right, that's the one right. So
Yeah.
that's not in here. That's another piece of the full Hamiltonian.
Yeah. To see h bar v q, we're only talking here about tunneling from layer to layer, and you're bringing up, okay, how does that match with the unperturbed Hamiltonian, which has Dirac points?
The diagonal output, not an output, but in a layer.
Yeah, but you actually end up with a more symmetrical model if you measure momentum from the Dirac point in each layer. And then you get these momentum boosts, or the 3 dominant processes. Okay, hungry?